Dear students, today we are discussing 5th semester core subject linear algebra. The chapter name is basis and dimension, contents, objectives, introduction, linear independence, basis and dimension, worked out exercises, summary. Next, objectives. First one, define the concepts of linear dependence and linear independence and quote certain examples. Define the notion of basis and dimension of a vector space and determine the dimension of certain vector spaces. Introduction. In the Euclidean plane, a vector and scalar multiples or parallel such vectors are called dependent vectors, which are not like that are called independent vectors. This leads to the concepts of dependence and independence in vector space. Linear independence. A subset S of a vector space V is called linear dependent if some elements of S is linear combination of others. There exists x belongs to S such that x equal to a1 x1 plus a2 x2 plus so on a n x n, where x1 comma x2 comma etcetera x n are elements of S other than the x, and a1 comma a2 comma a3 etcetera a n are scalars. In this case, x is said to be linear combination on x1 comma x2 comma etcetera x n. This is equivalent to saying that there are elements x naught comma x1 comma x n belongs to S and scalars a1 comma a2 comma etcetera a n not all zeros, such that a1 x1 plus a2 x2 etcetera a n x n equal to 0. Next definition. Let V be a vector space over a field F and S is subset are equal to V, then S is said to be linearly independent over F for any distinct x1 comma x2 comma etcetera x n belongs to S and a1 comma a2 comma etcetera a n belongs to F. F means F is a field. So, a1 x1 plus a2 x2 plus so on a n x n equal to a I, that equal to 0 for all I lies between 1 and n. This can be written as 1 less than or equal to I less than or equal to n. If S is not a linear independent over F, then we say that S is linearly dependent over F, and in this case there should exist distinct x1 comma x2 comma etcetera x n belongs to S, and non-zero scalars a1 comma a2 comma etcetera a n such that a1 x n plus a2 x2 plus a3 x3 so on a n x n. Example. Consider the vector space over R n over R as an example. Let E1 comma E2 comma etcetera E n belongs to R n. Be given E1 equal to 1 comma 0 comma 0 comma 1 0, E2 0 comma 1 comma 0 0 1, E3 0 comma 0 comma 1 comma 0 0 so on. So, E n equal to 0 comma 0 comma etcetera n. Then E1 comma E2 comma etcetera E n is linearly independent set over R for a1 comma a2 comma etcetera a n are scalars such that a1 E1 plus a2 E2 etcetera a n E n equal to 0. So, then a1 comma a2 etcetera a n equal to 0, then 0 element in R n, and hence each a I equal to 0. Example. Consider the vector space f of x of polynomials. Polynomials means algebraic expressions, nothing but over a field R, and let S equal to 1 comma x comma x2 comma x3 comma so on, then S is linearly independent over F. Next, check your C by P means check your progress. Determine which of the following are linearly independent in the vector space mentioned against them. First question. So, x 2 comma x 4 comma x power 6 etc. in f of x over f. Solution x 2 comma x 4 comma x so on in f of x over f. Solution x 2 comma x 4 comma x power x 6 is linearly independent in f of x over f for all a 1 comma a 2 etc. a n belongs to f such that a 1 x 2 comma a 2 x 4 comma a 3 x 6 plus so on a n x n equal to 0 and a 1 equal to a 2 equal to so on a n equal to 0. Next example, consider the set C of complex numbers. Then C is a field in which R is subfield. Therefore, C can be considered vector space over C as well as over R. Then set 1 comma I. What is 1 comma I? This is a complex number. What is complex number? Both real and imaginary numbers are called complex number. Complex number example a plus I b. So, a comma b are real numbers, I is the imaginary number, 1 comma I is a complex number, is linearly independent when we consider C over R and is linearly dependent when we consider C over C. If A and B are real numbers such that A dot 1 plus B dot I equal to 0, that means A into 1 plus B into I equal to 0, then A equal to 0 and B equal to 0, while we have 1 comma I linearly dependent, where we consider C over R. Theorem, most important theorem, let V be the vector space over F and S equal to x 1 comma x 2 comma x 3 etc. x n be subset of V, then S is linearly independent over F if and only if every element in linear span L of S, linear span means point of time. So, L of S has an unique representation of the form a 1 x 1 plus a 2 x 2 plus so on a n x n with x I belongs to S and a I belongs to F. X I belongs to S means S is a vector space, a I belongs to F means F is a field. Proof. Suppose S is a linear independent over F and let x belongs to L of S, then by definition of L of S, x can be represented as x equal to a 1 x 1 plus a 2 x 2 plus so on a n x n, while x I belongs to S and a I belongs to F such that x is expressed another form by taking some scalars to 0. We can assume that x equal to b 1 x 1 plus b 2 x 2 etc. b n x n, and now b I belongs to F. Now, we a 1 x 1 plus a 2 x 2 plus so on a n x n equal to 0. That implies a 1 x 1 plus so on a n x n equal to 0, since S is linearly independent over F and x belongs to S. So, we get that a I minus b I equal to 0 implies a I equal to b I for all I lies between 1 to n, that can be written as 1 less than or equal to I less than or equal to n. Thus, every element in L of S is a unique representation in the form a 1 x 1 plus a 2 x 2 plus a n x n belongs to S and a I belongs to F. Conversely, suppose that S is a linearly dependent over F, then there exists distinct x 1 comma x 2 comma etc. x n equal x n belongs to S, a 1 comma a 2 comma etc. a n belongs to F. So, F means field such that a 1 x 1 plus a 2 x 2 so on a n x n equal to 0. So, where at least one a I is not equal to 0, now the element x equal to a 1 x 1 a 2 x 2 etc. a n x is in L of S has two different representation namely namely x equal to a1 x1 plus a2 x2 plus an xn an xn and 0 into x1 plus 0 into x2 plus so on 0 into xn. These two different, at least one is non-zero. This is contradiction. Therefore, supposition that S is a linearly dependent is wrong. This completes the proof of the theorem. Example, let V be a vector space over a field F, then any x1 comma x2 comma etc. xn belongs to V are either linearly dependent independent over F or some xn is a linear combination of the preceding ones x1 comma x2 etc. xn. Proof: if x1 comma x2 etc. xn is a linearly independent over F, then there is nothing to prove. Otherwise, there exists a scalar a1 comma a2 comma etc. an, not all zeros, such that a1 x1 plus a2 x2 plus so on an xn. Let r be the largest integer in 1 comma 2 comma so on n, such that r is not equal to 0 and hence a1 x1 plus a2 x2 plus an xn equal to 0. xi belongs to S and ai belongs to F. xi belongs to S means here S is the vector space, F is a field. Hence, complete the proof of example. Corollary. What is corollary? Corollary is a sub theorem of the main theorem. Let S be a finite subset of vector space V over a field F, then there exists a subset B of S such that B is linearly independent and L of S equal to B. So, proof: this is simple consequence of the above corollary. If S is a empty or S equal to 0, then take B to be empty. If 0 is not equal to X belongs to S, then X is linearly independent over F, and hence there exists subset B of S such that B is linearly independent over F and L of B equal to L of S. Basis and dimensions. In any vector space V, subset which are both linearly independent and span the whole V play a very important role in the study of vector space. We shall discuss such subsets in the vector space. Definition: let V be vector space over a field F and B be the subset of V, then B is called the basis for V over F. If B is linearly independent over F and the linear span L of B equal to V. Theorem: let B be a basis for vector space space V over a field F if B is subset are equal to C is subset are equal to V, where C is linearly independent over F, then B equal to C. Also, if F subset are equal to B and L of S equal to B, then S equal to B. Otherwise, B is maximal linearly independent set and is a minimal set whose linear span is V. So, proof: let B subset are equal to C subset are equal to V and C be linearly independent over F. Let X belongs to C. Since L of B equal to V and X belongs to V, we can express X as linear combination of elements of B, that is X equal to A1 x1 plus A2 x2 plus A3 x3 plus so on an xn, where x1 comma x2 comma etc. xn are distinct elements of B and ai belongs to F. Since B is subset are equal to C, we get x1 comma x2 comma etc. xn cannot be distinct, that x must be equal to for some I, for hence x belongs to B. Therefore, C belongs subset are equal to B. Suppose S is subset are equal to B and L of S equal to B. If S is not equal to B, then there exists Y belongs to S, since Y equal to B1 Y1 plus B2 Y2 plus so on Bn Yn Here B subset are equal to we get x1 comma x2 comma xn cannot be distinct, x must be equal to the for some I, for hence x belongs to B. Therefore, C is subset are equal to B. Suppose S is subset are equal to B, C is subset are equal and L of S equal to B, S is not equal to B, then there exists Y belongs to S, since Y equal to B1 Y1, B2 Y2 etc. Bn Yn, where Y1 comma Y2 comma etc. Yn Ym are distinct elements of S. Bi belongs to F, F means field. Here Y1 comma Y2 comma Yn are distinct elements of B, and B1 Y1 plus B2 Y2 plus so on Bn Yn equal to 0, which is contradiction to the fact B is linearly independent. Thus, S equal to B, this completes the proof of theorem. Next theorem, this is also most important theorem. Suppose B equal to x1 comma x2 comma etc. xn for the basis for a vector space V over a field F, and y1 comma y2 comma etc. yn is linearly independent set in V, then M is less than or equal to n. So, we have y1 comma y1 belongs to V, that equal to L of B, and hence y1 is a linear combination of x1 comma x2 etc. xn, and therefore, the set S1 equal to y1 comma y2 comma etc. yn, again x1 comma x2 comma x3 etc. so on xn is a linearly independent, since yi is a linearly independent subset, and such that B is subset are equal to S. Both linearly independent includes and excludes at least one x1. Now, consider S2 equal to y2 union T1, that equal to y1 y1 comma y2 comma y3 yn, x1 comma x2 comma x3 xn. So, here we have y1 comma x1, so y1 comma xn. So, y1 comma y2 belongs to T2, T2, then T2 is a basis for V, We get basis which includes at least one xi's, at least m number of S, m minus 1th stage. The basis contains y1 comma y2 comma etc. ym minus 1, and also contains at least xi's, otherwise y1 comma y2 etc. yn is a basis, therefore, is a linear combination of y1 comma y2 etc. yn, which is a contradiction. This implies that m minus 1 less than or equal to n minus 1. Here both sides, left side and the inequality cancel the left sides and right side. So, and hence m is less than or equal to n. This completes the proof of theorem. Definition: a vector space V is said to be finitely generated if there exists finite set S equal to x1 comma x2 comma etc. xn in V, whose linear span L of S is equal to V. If V is finitely generated and L of S equal to V, then S contains basis. This shows that any finitely generated vector space has a finite base. Theorem: any two bases of finitely generated vector space have the same number of elements. Proof: let V be the finitely generated vector space over the field F. V should be possess a finite basis B equal to x1 comma x2 comma etc. xn. If C is other basis, then C must be finite less than or equal to n. By the same argument, n is less than or equal to mod C, hence n equal to mod C. Definition: let V be the finitely generated vector space over a field F, then the number of elements in any basis is called the dimension of V over F, and it is denoted by V or simply dimension V when there is no ambiguity. Ambiguity means lack of clarity, lack of clarification, lack of clarity about the scalar field F. Finitely generated vector space is also called finitely dimensional vector space. Example, consider the field C of complex numbers and the field R of real numbers. Then R is a subfield of C. What is C here? C is a complex number. C is a vector space over C, means complex number is a vector space over complex number, as well as over R. We have 1 is a basis for C over C, while 1 comma I is a basis for C over R. R means set of real numbers. Therefore, dimension C equal to 1 and dimension F C equal to 2. So, for any field F and positive integer n, Fn is a vector space over a field F for any I lies between 1 and n. This can be written as 1 is less than or equal to I is less than or equal to n. Let Ei be the element in Fn whose ith coordinate is 1 and all other coordinates are zeros. Then E1 comma E2 comma etc. En is a basis for over F, and hence dimension F equal to 1. Dimension F equal to 1. Let V be a finite dimensional vector space over a field F. Then any linear independent set in V can be extended to basis. Proof. Let A equal to x1 comma x2 comma etc. xn be a linear independent set in V. Then M is less than or equal to dimension V. If A is not basis, then L of A is not equal to V, and hence there exists an element x m plus 1 in V such that is not a linear combination of elements in A, and hence x 1 comma x 2 etc. x m plus 1 is a linear independent. If this is not a basis, then we get another element which is not combination of x 1 comma x 2 comma etc. x m comma x m plus 1 in V such that x 1 comma x m etc. x n is a basis for V. This completes the proof of theorem. CYP. CYP means check your progress. Let F be any field and V be a vector space of all m cross n matrices over F. Then determine the dimension of V over F. Solution. For any I lies between 1 to m and j lies between 1 to m. This can be written as 1 less than or equal to I less than or equal to m, and I less than or equal to j 1 less than or equal to j less than or equal to m. Here what is I and j? I is the ith row, j means jth column. So, E I j be the matrix whose ith I j at entry is 1, means ith row jth column entry is 1 and all other entries are zeros. Then E I j such that I lies between 1 to m and j lies between 1 to m is a basis for V, and hence dimension V equal to n m, hence the solution. Theorem. Prove that any linear independent set in any vector space does not contain the 0. Proof. Let S be a linear independent set in vector space V if 0 belongs to S. 1 into 0 is 0, and by the definition of linear independence we should get the 1 equal to 0 in F, and hence F equal to 0. A contradiction, thus 0 does not belong to S, hence proved. Theorem. Most important theorem. Let V be a vector space of dimension n, then prove that any linear independent set in V with n elements is basis. Proof. Let B equal to x 1 comma x 2 comma etc. x n be linearly independent in V. If B is not basis, then L of B is not equal to V, and hence there exists x n plus 1 in V, which is not linear combination of x 1 comma x 2 comma etc. x n, and so that x 1 comma x 2 comma etc. x n plus 1 is linearly independent. This contradicts hence proved. Problem. Yeah. So, for short answer type 5 marks question, most important, let x1 equal to 3 comma 1 comma 0 comma 0, x2 equal to 0 comma 2 comma minus 1 comma 0 and x3 equal to 0 comma 0 comma 4. Prove that x1 comma x2 comma x3 linearly independent in the vector space over R. Working rule is generally we need to do a1 x1 plus a2 x2 plus a3 x3 equal to 0. So, if you get all a1, a2, a3 zeros, then we will say given problem is linearly independent in the over space. So, solution you will see. Suppose a1 comma a2 etc. an belongs to R such that a1 x1 plus a2 x2 plus a3 x3 equal to 0. Note that 0 on right side of the above equation is the 0 elements 0 comma 0 comma 0. We have a1 first x1 3 comma 1 comma 0 comma 0 plus a2 second point, a3 third point, that equal to 0 comma 0. If you equate the equating LHS to RHS, you will get 3a1 comma a1 plus 2a2 comma minus a2 comma 4a3, that equal to 0 comma 0 comma 0. On simplification we obtain a1 equal to a2 equal to a3 equal to a4, a3 equal to 0. Thus, x1 comma x2 x3 linearly independent, hence the solution. Theorem, let V be the finite dimensional vector space over a field F and W be subspace of V. Prove that V equal to W. So, proof, let dimension V equal to n, that equal to dimension W, B equal to x1 comma x2 comma xn and C equal to y1 comma y2 comma yn be a basis for V and W respectively. W is not equal to V, then linear span L of C subset are equal to W, subset are equal to V, and hence there exists a elements yn plus 1 in V such that yn plus 1 does not belongs to L of C, then y1 comma y2 comma etc. yn plus 1 is linearly independent set in V, and hence n plus 1 less than or equal to n, which is a contradiction, then W equal to V, hence proved. Theorem, let f be any field and f of x be the set of all polynomials over f. Then f of x is a vector space over f, then prove that f of x is not finitely generated over f. Proof, suppose f of x finitely generated over f, then there exists polynomial f1x comma f2x comma so on fnx in f of x. Choose an integer m such that degree fi of x less than m for all I lies between 1 to n. Then x power m is an element in f of x and x power m is not a linear combination of f1x comma f2x comma etc. fnx, which is a contradiction. Thus, f of x is not finitely generated, hence proved. Theorem, let f be any field and n be any fixed integer, let w equal to a naught plus a1 x1 plus a2 x2 plus so on a n x n belongs to f of x. So, a naught plus a1 plus etc. plus a n equal to 0. Prove that w is a subspace of f of x and find basis for w. Proof, clearly the 0 polynomial belongs to w is not empty, let f of x into g of x belongs to w and a comma b belongs to f. F of x equal to a0 plus a1 x1 plus a2 x2 plus so on a n x n, and g of x equal to b naught b1 x1 plus b2 x b n x n. Now, a f of x plus b g of x equal to a0 plus a1 x1 plus so on a n x n. So on b b0 plus b b1 x1 plus so on b n x n, that implies a f of x plus b of x b g of x belongs to w. Thus, w is a subspace of V. Let us find basis for w. F naught 0 equal to 1 minus x1, f1 equal to x minus x1, fn plus 1 n minus 1 xn. These are elements of w and basis. So, f naught x1 f1 x is a basis for W over F and W equal to N. This completes the proof of theorem. Thank you very much.